All right, section 5.4, talking about quadratics, completing the square. So getting a little bit more advanced here. Usually we just try to factor problems to solve them or find roots or zeros. But as it says here, many quadratic equations contain expressions that cannot be easily factored. For equation containing these types, we have to use other methods. And one way is using square roots and finding roots. So let's kind of jump right in and get rolling. So 5.4, square root property. So the first thing is with the square root property is that when you take the square root of a number, for instance, you say, hey, what's the square root of 16? Normally we would just say 4. That's called the principal square root. But technically, the square root of 16 can be positive or negative 4. And the reason being is because 4 squared will give me an answer of 16. But negative 4 squared will also give me the answer of 16. So the square root property says you always have to take into account the positive or the negative of that answer. So for instance, when I'm solving an equation like this one, I notice there's no x term. So you're going to use this property a lot of times when you have an x squared term and you have a constant or a number, but no x term. So here's what you want to do. You want to isolate the x squared term. So first thing I'm going to do is I'm going to try to add this 4 to both sides. And I get 3x squared equals 72. And then I'm going to divide both sides by 3. Divide by 3, divide by 3. And I get x squared equals, and I believe that's 24. Now this one's not going to be a perfect square because the square root of 24 is like some decimal. So we're going to simplify it like we did back in chapter 1. So when I take the square root, that undoes this exponent too. So I just end up with x. And then my answer is going to be the positive or negative of the square root of 24. Now, if it's a certain application, you might want to go into decimal world, but we're actually going to simplify that square root. So the square root of 24 can be broken up into, 4 goes into there 6 times. So that's really just the square root of 4 times the square root of 6, or 2 radical 6. So another way to write this would be plus or minus 2 radical 6. Another way that we did it, if you remember back, we did like a factor tree kind of thing. And we just said, how can we make 24? Maybe 2 and 12. Can't go any further with 2. 2 and 6. Can't go any further. 2 and 3. And then what we did was we gathered up every pair, went on the outside. And then the loners went on the inside of the radical. And then we multiply those together. And that's another way to get 2 radical 6. The first method was I identified a perfect square and I yanked it out. Something you might want to just kind of refresh yourself with, you might want to write right up here, is perfect squares. So those are the numbers like 2 times 2, 3 times 3, 4 times 4, 5, 6, 7, 8, 9, 10, 11, and 12. That's probably enough. But those numbers should jump out at you to know that they make nice, perfect roots when you take the square root of them. All right, next example, number 2. This example isn't really how I would probably solve this problem. Normally, I would solve this problem. Let me just kind of explain. If somebody just said, hey, Kraft, solve that problem, I normally try to set the quadratic equal to 0. So don't write this down. This is just me kind of thinking out loud. But normally, I would leave the left-hand side alone, and I would move that 27 to the other side. So I would end up with a minus 2. And then I would try to factor it. And I would try to factor it like we did in 5.3, but then I'd be like, well, wait a minute. I can't get 2 numbers that times together to make 2 and add together to make 10. So I would probably go into what's called the quadratic formula, which we're going to learn later on in this chapter. But they want you to see that over here on the left-hand side, this is a perfect square. So remember, when you're talking about trinomials, a perfect square is something that, you know, for instance, this one is really just x minus 5 times itself. Now, a lot of people probably won't just look at that and just understand that, hey, there's a perfect square. But it actually is. It's actually x minus 5 times x minus 5, which can be written like this. All right? So if you are able to recognize a perfect square, you could factor it straight to here. And now I'm like, hey, I can get rid of that 2 exponent. I can just take the square root of both sides, which completely undoes this 2. But then if I take the square root of that side, I got to take the square root of this side. And when I clean this up, and remember it's positive and negative, I would now, to solve for x, I would add the 5 to both sides. And you can't add a number to a radical. So I would say, well, this is going to be 5 plus or minus the square root of 27. Now, we also could simplify the square root of 27. You know, 27 can be broken down as 9 times 3 and 3 times 3. So remember, pair of 3's, count it once. A loner 3, put it inside. So this is really 3 radical 3. So if we were to simplify this problem down as far as it could go, we will get that answer. So even though I probably wouldn't solve this problem this way, I thought it was a good idea to sneak it in there because you could solve it by using square roots, but probably won't do it that way too often. All right, but why I showed you this is because there is a way, if I want to, I can create a perfect square if I want. So let's go down to the next one. And it says the expressions above happen to be perfect squares. You can use algebra and a method called, so this is the title of the lesson, a method called completing the square to force any expression into a perfect square. So let me just kind of make up some examples. All right, so let's make an example. One example of a perfect square would be something like, you know, x plus 3 times itself, all right, which is x plus 3 times x plus 3. And if we did FOIL and we worked it out and did you know, all of this type of stuff, we would end up with, when it was all cleaned up, x squared plus 6x plus 9. So notice the relationship between our trinomial and what we started with. All right, I just kind of want you to look at the numbers there and kind of see the relationship. Now I'm going to do another one. I'm going to do a new one. Let's try, I don't know, let's maybe do x minus 7 squared. All right, and I'll kind of skip this middle part, but it's going to shake out to be x squared minus 14x plus 49. So there's a relationship between the middle term and this number. And there's a relationship between the middle term and this number. And you'll notice that it's always half of it. It's always going to be half of that number. So whenever you want to do the shortcut and square something, you basically double it and then you square it for the back part. So it's always kind of, you know, it's kind of x squared plus double the x plus, then you square that number there at the end, whatever the amount is. So I'm going to just kind of break down completing the square. So here's kind of how we do this. To complete the square, what you're going to do is, remember our numbers, you know, this is A, which is 1, B is 2, and C is what this back part is. Well, to complete the square, what you're going to do is you're going to chop B in half. You're going to do B divided by 2, and then you're going to square it. So we're going to do B divided by 2. So that's 2 divided by 2, which is 1. And then you're going to take that number, and you're going to put it up here, and you're going to square it. So I've just created a perfect square here. And I could go back and I could check it out, and if you verify, it is x plus 1 squared. Like that's what it would shake out to be if I multiplied it out. So I'm going to do this one right here. Basically, this is my b. I divide it by 2. So I don't need to write it, I guess, but I'll do b divided by 2. So negative 8 divided by 2 is negative 4. And then I'm going to square that negative 4. And it's going to be a 16. Okay? And if you check it out, this is x minus 4 squared. I made it be a perfect square. All right? I made it work out that way. This one over here is a little trickier because unfortunately in this case, b is odd, which is kind of a problem because when you divide it, you're going to get a decimal. So depending on which route you go, when I do b divided by 2, I'm either going to get 2.5 if you want to go to decimal world, or I'm going to get 5 halves if you want to go into fraction world. And depending on how I square it, I could get 2.5 squared. When I put that in here, that's going to be 6.25. Or if I wanted to do the 5 halves times itself, well, that's going to be 25 over 4. So either way, those two are going to complete the square. And, the actual factoring is going to be x plus 5 halves squared. That makes it a perfect square. Now, you're kind of like, why are we trying to do this? Like, why are we trying to complete this square, come up with this back number? And I'll show you because it's going to make factoring a little bit easier. So solve each equation, whatever, get rid of that. Solve each equation by completing the square. So what you're going to want to do is, first thing, I'm going to kind of write this out in steps. So step 1, and maybe I'll go up since we had a little bit of white space up here. I'm going to kind of put some steps here. And actually, I had a picture that doesn't seem to be here anymore. So I think in the notes that I gave you guys, it was definitely in the notes today. So I'm going to pull up a picture. So just bear with me 1 second. I'm going to stop this video and grab a picture. All right, so here's the original picture that's on the notes that I printed for you guys, and somehow it didn't come through on the PDF. But I'm going to kind of help you follow the steps. So they're in your notes. So step 1 says collect all the variable terms. That means everything with an x in it on one side, and put your constant or your numbers on the other. So I'm going to rewrite this one, and I'm going to move this 6x to the left side. So I'm going to have x squared plus 6x equals 27. All right, so that was step 1. As needed, divide both sides by a to make the coefficient. So we're already sitting pretty good because our a value, there's no number in front of x squared. So we're in pretty good shape. So we don't have to do step 2. Complete the square by adding b over 2 squared to both sides. So b over 2 squared means I'm going to take this 6 divided by 2, which is 3, and then I got to square that. So I'm going to add that. But if I just add it to the left, to keep the equation balanced, I also have to add it to the right. So that came out to be 9. Half of 6 squared is 9. So what I'm going to do is I'm going to take that number and I'm going to add it to both sides. So I had x squared plus 6x. Now I'm going to add 9. But if I do it to the left-hand side, I also have to do it to the right-hand side. All right? Because, making sure to do this keeps my original equation balanced. So I got that going on. Well, the whole point of me doing this was so that I could use square roots. So I'm like, well, I just made this a perfect square. So I should be able to factor it pretty easy. That's just x plus 3 times itself. It's always going to be this number. That's what's always going to go, over here if it's positive. So that's x plus 3 squared. On the right, I have 36. And this one comes out to be pretty nice because now we can solve it like we did earlier in the notes. And let me just make sure I'm following the steps. We completed the square. We didn't need to do this. We factored it, yep. And now we're going to take the square root of both sides. So I'm taking the square root of both sides. And that just wipes out the 2, so I'm left with just the x plus 3, which is nice. And the square root of 36 is plus or minus 6. Positive or negative 6. Now we got to solve both cases. And I know I'm creeping over into this other problem, so hopefully in your notes you're not. But I have to solve 2 cases. I have to solve, well, when is x plus 3 equal to 6? And then I also have to solve, when is x plus 3 equal to negative 6? Because remember, there's 2 roots for all these problems. And subtracting 3 from both sides gives me that answer. Subtracting 3 from both sides gives me this answer. So those are my zeros, or those are my roots, or those are the answers to the equation there to the left. 3 and negative 9. All right, so let's try another one. We'll try this 2x squared one. This one's going to be a little bit trickier. So I'll kind of try to write this out in order with steps. So step 1, collect all the variable terms on one side. This is already done. When I look at this problem, I have the x squared, I have the x. The constant is over on the right. So step 1 is done. So step 2 says, divide both sides by a to make sure that we have an x squared term. So when I'm looking at this, so right now I have this equation. You can't complete the square until your x squared term is a 1. So what I need to do is, for step 3, or for step 2 I need to divide everybody, both sides. So everybody's got to get divided by 2. So this isn't hurting the equation. As long as I divide everybody by the same number, I'm not hurting anything. So what I'm going to get from that is I'm going to have x squared plus 4x equals 6. All right. So I've done step 2. So you're done, you're done. Now I got to complete the square. So complete the square is, I'm going to have x squared plus 4x. To complete the square, remember, I got to chop b in half, which would be 2, and then I have to square it and put it to both sides. So 2 squared is going to be adding a 4 to this side. But then if I add it to that side, I also have to add it to this side to keep the equation balanced. So you're done. Now I should be able to factor, because I have a perfect square here. You know, this is x plus b, or x plus 2 squared, is 10. So I factored it into a perfect square. That's step 4. Step 5 is take the square root of both sides. So take the square root. So step 5 is about to happen right now. Take the square root, take the square root, and I get x plus 2 equals, well, I don't think there's any way to break 10 down, because 10 is 2 times 5, and there's no pairs, there's just 2 loners. So I think square root of 10 is the best I can get, but I do have to remember to do plus or minus the square root of 10. And now if I subtract 2 from both sides, I'm going to get x equals a negative 2 plus and minus. I don't know why I put a 2 there. It's just being goofy. Square root of 10. Boom. So sometimes you're going to get these weird answers where you're going to have a radical in your answer. And that happens on the SAT too, so that's fine. All right, another time you're going to want to complete the square is, let's say you have to convert into vertex form. So let's say somehow you get an answer, or you're given a problem and it's in standard form, which is the way these two are written, and you want to change it to vertex form. Just remember from 5.1, vertex form was, a times x minus h squared plus k, and it was really nice because it told us like where the vertex was. You could just see it. So what you're going to do is you're going to set this thing up and you're going to say, okay, f of x equals x squared plus 10x, plus, and here's where you're going to have like, your box. And then we have a minus 13 here that we can't forget about. All right. So let's think about completing the square. So ignore your constant for a second. If I want to complete the square, I'm going to take b, which is 10. I chop it in half, which gives me a 5. And then I got to square it and put it right in here. So that would be 25. But, you know, I have a function here, an equation, that I just added 25 to the right-hand side. And if I still want it to be a function, like I want to just rewrite this so it's still f of x over there, in order to make things right, since I just added 25, I'm going to take away 25. And that'll basically keep things balanced. I added 25, but then I took it away. So then here's kind of what happens. You know, this portion right here can now be rewritten as x plus 5 squared. And then over here, I got to kind of clean these two up. That's going to be a negative 38. So now we're looking at like, oh, we're like, okay, we're back in vertex form. So I could see for this problem that the vertex lives at opposite same. So for this problem, the vertex would be at negative 5, negative 38. So if you need to, you can change any problem into vertex form if it's in standard form. Now, I don't know if I would do that, like graphing it. I would probably just use what we learned in 5.2 and do the negative b over 2a thing, but you could. So let's try it again on this next problem. I'm just erasing to give myself some room. So again, I have h of x equals x squared plus 24x. I'm about to do something to it. I have the plus 145. So complete the square, chop this middle part in half and square it, which is going to be add 144. Keep things balanced by taking away 144. All right. Clean it up, factor this, which it should just be x plus 12 squared. It's a perfect square. The plus 145 minus 144, well, that's plus 1. And now we have a nice function written in vertex form where the vertex is going to be at negative 12. I don't like that 2 there. Clean that up. At negative 12, positive 1. So this would be the vertex. So that's a quick, easy way to convert from standard form into vertex form by using this new method, completing the square. I'll be honest, this method isn't like high up in my toolbox. I factor probably 95% of the time, and when I can't factor, I use what's called the quadratic formula, which is coming later this chapter. But completing the square does have its time to use, particularly on some SAT questions that I'll show you once we're a little bit further in. All right, hope this helps you with the practice. See you.